So, hi everybody. My name is Seamus Delaney. I'm here to introduce the final session. Yes, final session of the November lectures, and with our two fantastic presenters. I'm being a little naughty though. I have arranged to steal 1 minute of your time to introduce something that the Chemistry Education Association have graciously financially supported this year and next year as well. So I've got one slide. It is the Chemistry Education Research Professional Learning Communities. Essentially, in 1 minute, it is financially supported by the CA. It's free for chemistry teachers here in Victoria. It doesn't matter what sector you're from, it's free. This year, we obviously had to deal with COVID, and next year that will still be a reality of dealing with online and a combination of online and face-to-face. So it's going to be 2 days of professional learning, 1 day at the start of the year and 1 day at the end of the year. And essentially it is a mentor-supported program where we get we introduce some really top-of-the-line chemistry education research to you. Areas that teachers worked with this year was on sustainability, on scientific literacy, on reading comprehension, situating integrated curriculum. So there's lots of great things. And we get you into little groups of teachers. We take about 10 to 15 each year. We get you into nice little groups, and then we support you throughout the year to essentially implement some sort of research-informed activity in your classrooms. But importantly for us, we encourage you then to think about who you could present this to. Who's your audience? Find your audience, feel like you're becoming part of the professional learning community. And just to wrap it up, the groups that we've had from this year, 2 of those groups are presenting at STAV VCE Chem next year. So, paying it forward to, get the fantastic things that they've been doing and getting it out. So can I emphasize it is free? The only thing you really need to do is make sure that your principal is okay with you doing that, because after all, it's 2 days of PD with a few online meetings along the way. There is an expression of interest. It's there on the slide. So bit.ly CEAPL 2021. I'll put it in the chat, and also I'll put in the chat a little video that shows off a few of the things as well that have happened this year. Okay. Any questions at all? Go to that website and shoot me an email. More than happy to. So again, we're looking for 10 to 15 people to be involved. Now I need to go back and stop sharing screen. So now I have the fantastic duty of introducing our 2 speakers. I'll just introduce them because I think they'll do a much better job of introducing what's happening. So in no particular order, I have Drew. So Drew Chan is currently a VCE and IB chemistry teacher at Presbyterian Ladies College, and will be the head of chemistry starting in 2021. He's been lead author for Hyman Chemistry 1 and 2, 5th edition. So he's also in the authorship team for the 6th edition. And, along with all his teaching and textbook writing, he has also he's our previous president of the CEA. The previous president of the CEA is Lanna, Derry, who has been teaching VCE chemistry since 1991 and HSC chemistry before that. She is currently the head of science at Tintern Grammar and has been involved as an author, a lead author of 7 VCE and IB textbooks. She's also part of the CEA author team and is also the organising author for the 6th edition that's coming out for the new VCE chemistry course. So I'm going to hand over both to them. So thank you again for your time today, and I really hope that everyone enjoys today's workshop.
Okay, I'll take over from here. Thank you, Seamus. Thank you so much. So this afternoon, Drew and I are going to attempt to lead a discussion about the exam that was sat by the students on Monday. We want you to know that we're not presenting ourselves as the ultimate experts. We're not marking. So, we're not the people who will be marking this exam. We do not know what is on the mark scheme. these answers or suggestions of how students would go about answering these questions are purely our opinion and do not reflect the opinion of any other organisation. We're going to try to talk to you in answering any questions, but questions that you want to put on the chat, when one of us is speaking, because we're going to very much work as a team, when one of us is speaking, the other will be monitoring the chat, but we won't answer the questions on the chat. We'll you know, chip in when there's an opportunity with a summary of those questions and answer them verbally. So to try and give the most general way of dealing with things rather than getting all these very particular answers. And I know even as I'm talking here now, having answers coming up on the chat can be quite distracting. Mr. Delaney, Seamus. So without further ado, let's see how many questions we can get through. We have the data that Seamus collected, not Seamus,
Nick.
that Nick collected from all of the, or everyone who was interested in responding to the survey. So Drew, do you want to kick things off?
Well, I could see that the most requested question for, we're going to start with part B, I think, because maybe it might be more valuable to talk about part B. And I think most people want to talk about question 10 first. That was the most requested one. So I was going to bring up my version of my copy of the exam.
So if you've got your paper copy of the exam, it'll be handy to have it open to question 10, which was the last page. And while Drew's doing that, the question was asking about classical and instrumental methods for determining the chemical composition of a compound.
Yeah.
Have you found it?
Yep, I found it.
Okay.
So yeah, it's a 3-mark question, but with a lot of these questions, which are very sort of open-ended, I'm sure that the markers will be looking for, you know, there might be 5 or 6 things that are possibly part of the answer there. So sort of one thing I was thinking, you know, in terms of they're focusing really on, these, what are they called? The classical methods of analysis. So something that, you know, the students would have done in class would have been to react an alcohol with an acidified oxidizing agent. And so, for example, using acidified permanganate and looking, you know, just for that color change from purple to, say, orange or colorless, which might indicate that, the compound is able to be oxidized, so it could be an alcohol. So that might be, you know, a starting point. And then more specifically, you're looking at then testing to see if the students understand if you oxidize a primary alcohol, you'll produce a carboxylic acid under, you know, reflux conditions, or whether you can oxidize, if you oxidize a secondary alcohol, you get a ketone. So that's sort of answering that first dot point there, asking about, determining whether it is an alcohol and then whether, you know, what type of alcohol it is. Do you have anything more to add there, Lanna, in terms of those things?
I was going to say one thing, Drew, and I hope you don't mind me saying, when you knock your microphone, it makes quite a distracting knocking sound.
Always. Thank you for letting me know.
So the only thing I'd say, and this is something that bothers me when I look at these exams as a student, is that in the VCE syllabus, students are required to know what a primary alcohol is. They actually aren't required to know a secondary and a tertiary alcohol. So I do feel if anyone is starting to worry when they were listening to Drew, that I doubt that the mark scheme or the examiners will be expecting a reference to secondary or tertiary alcohol. They'll just be saying, yes, primary alcohol or not. That would be my normal experience when I have been marking. And then the the quantitative analysis, they'd be expecting, because redox titrations are very much on the syllabus, the study design, there'd be an expectation of suggesting a redox titration, once again with the dichromate solution, to determine how much ethanol or alcohol, sorry, was there. So I think the 3 marks, there's going to be, I'm not sure whether you said this, Drew, there's going to be a lot of scope for marks being allocated. There's not going to just be 3 correct marks.
Lanna, there's a question in the comments about wouldn't that be covered in the production of a ketone, aldehyde and carboxylic acid? If a student needs to know how to produce a ketone, wouldn't they need to know that it comes from a secondary alcohol?
Well, yes, of course they would, but it's not explicitly stated in the study design.
And Jenny, and there's another comment saying that the students had to draw a tertiary alcohol earlier on.
I know. Well, I won't bring up the study design now, but I'm pretty sure the only reference is to a primary. But we'd have to, if we look at question 3, by the way, hello, Jenny. Question 3.
Yeah, I remember question 3, it was draw a tertiary alcohol.
Yeah, but did it name it exactly as a tertiary alcohol? No. Oh, yes, and that's it does. Ooh. Yeah, that's ugly. I don't know, I'd have to, look, there's not a lot we can do. The exam's written, and this is always something that's said at the markers meeting as well. The exam is written. The job of the markers is not to critique the exam, nor is it our job. But I don't think that there would be a need for explicit reference to secondary or tertiary. That would just be, so don't worry about that. I think that's the bottom line.
Yeah, I think the study, if you look in the chat, Lanna.
Yes, Angela's just said that, yeah.
So apparently, so there might be actually is mention of primary, secondary and tertiary alcohols in the study design.
Yeah. I'm so sorry. I must have been thinking about a previous version. Sorry.
Okay. Yeah.
My apologies. Well then they're going to have to give all the details. There we go. Let's move on. Heaven help them.
So again, with B.
Sorry, before we go
Lanna,
on,
go ahead.
There's been a couple of requests saying, where can we get a copy of the exam if we don't have it? It's not published yet online. I think probably the best thing is you're best off with a hard copy from your school. So do ask your VCE coordinator if they have a spare copy. And
the comment is saying maybe check with your VCE coordinator.
Yeah, which I just said.
And
someone else has said that school was giving a link.
Facebook.
Oh, yeah.
Yeah. So there are several places.
Yep. All right. Okay. So we've established tertiary alcohols mentioned. So there's no need for anyone else to say anything more about that. And Facebook, or try and get a hard copy from your coordinator. Okay, let's move on. Drew, do you want to talk about part B?
Yeah, so part B, I guess the distinction is we're looking at the distinction between a ketone and a primary alcohol. So I guess the 4 marks, the way I sort of picture it is the 4 marks will come from discussing IR and what you're going to see in the IR spectrum for the ketone. And so the 1 mark will be, say, identifying an absorbance band at 1680 to 1850, which corresponds to the carbonyl for a ketone, versus for a primary alcohol, you're going to see an absorbance band at 3200 to 3600 for the OH of an alcohol. So that would be, 2 marks, I would think. So the two different key features in the IR spectra. And then I think for the NMR, you're looking at the ketone. I think the ketone with that formula is propanone. And so there'll only be one peak with no splitting because the two CH3s are equivalent. Whereas with the primary alcohol, well, again, we don't know what primary alcohol it is, but there'll be multiple peaks. Okay, so that's the distinguishing feature between the two.
Drew, there's been a question, and I was just thinking, so one of the things that when Drew and I first looked at this question together, our first reaction was that we'd expect our students to draw the structures so that they could focus their thoughts. And if you try to draw the primary alcohol, the only way that you can draw it as an alcohol is to have a double bond. If it's got single bonds, it's not going to have six hydrogens. It'll have 8 hydrogens. So they've got to work out that it's got a double bond. And they may even bring that up in their discussion of the infrared spectrum. But then once they do that, then they can talk about the number of peaks on the NMR spectrum from, their structure. They can refer to that.
Yeah, sure.
But it's always a good idea for students to draw these organic structures. George has brought up a question in the chat, and it goes back to multiple choice 21. Amides weren't removed from the study design. It was the condensation reaction that made an amide that was removed from the study design. So that question was still perfectly valid because the amide functional group was still in. So that's what that question was about. So that just answers that one. And Braden is asking about interpreting principles. In this question, Braden, I'm assuming?
Yeah, I think he's talking about in this question. So explain how the principles of IR spectroscopy lead to different spectra.
Well,
I think that the study design doesn't really need the students to know a lot about the. Well, they're not actually. They're not saying.
I was going to say, I guess the principles of infrared spectroscopy, in that a functional or a bond is absorbing energy, and so we would be pointing to the particular bonds. I think that's the way in which they'd be expecting principles to be interpreted. Yeah. Is there anything else anyone wants about question 10, or shall we move on? Well, is there anything anyone else wants? Anything in the chat? Doesn't look like it. Let's move on. Question 9. All right. Drew, do you want to start?
Just scrolling up.
Oh, you're scrolling. Okay. So question 9's on the previous page.
All right. So we're not going to, Lanna and I have had a good chat about the actual experiment itself. And we're not here to critique whether this experiment would actually work or not. We're just going to try and answer the questions. So I think for 9A, to be honest, I haven't actually written 2 things there.
No, me neither.
I just, I mean, maybe I'm being a bit lazy. I just haven't sat down and written two things, but certainly I would imagine there would be something along the lines of wearing, personal protective equipment would certainly be a basic, fundamental, important thing.
But probably better to be explicit.
Yep.
Safety glasses.
Yep. Just trying. Yeah, I'm sure. Lanna, would you offer up? Could you think of something else that students would typically write there that would be, valid and reasonable and explicit enough?
I was wondering whether the hazard of breaking glass would be something that could come up there. If the pressure from the 10 ml of acid builds up to such an extent that something breaks, I don't think they would accept, well, a well-ventilated room, not really needed, it's carbon dioxide. Okay, Peter has suggested care when fitting the balloon, and cutting themselves on the glass.
Yeah. maybe, because they're starting to get to 45 degrees, is there any sort of hazard in terms of
Well,
burning themselves or,
or hot acid. I mean,
spilling hot acid on yourself?
Yeah. So Nick Derry has said, what about doing a risk assessment? As in conducting a risk assessment, yeah. Is that, yeah, because then the student is complying with safety guidelines by writing a risk assessment? Not sure.
Possibly.
Yeah. Disposal of wastes. Well, the wastes are pretty dilute and are pretty safe. I guess disposing with lots and lots of water. Yeah. So it's probably the hot acid being of a particular danger.
Yeah,
so,
I'm just wondering whether, Lanna, they're going to be very generous and just go, something like 1 mark for wear a lab coat, 1 mark for wear safety glasses, or is that's just not good enough?
Well, in my experience, lab coats not always listed because not all schools have lab coats. So it would be accepted, but it wouldn't be the only required one. Said, hopefully they wouldn't be looking for gloves, but certainly the taking care, washing up spills of acid, diluting with water, all of that sort of thing.
Yeah.
So usually in the safety questions, most things are accepted.
Yeah, as long as it's reasonable and yeah.
Then when we were going through this, we thought, well, the independent variable was straightforward. It was the temperature of the acid.
Yeah. Thank goodness there actually is an independent variable.
Yay! Yes, it's a proper investigation. Well, they only do it once each, but never mind. The dependent variable, how it's measured. So I was thinking about this after a discussion earlier, and I think the dependent variable is meant to be the rate of production of CO2.
Oh, okay.
Because the aim says to find out how the temperature affects the rate of production of carbon dioxide. So how independent variable affects dependent variable.
And then, well, I guess that would be your first mark.
Mm.
And then how would you describe how is it measured?
Measured by measuring the temperature. Oh, sorry, the time taken for the reaction to occur.
Would for that one, Lanna, if you're saying rate, would you need to say, you need to actually measure both the balloon diameter and then also the time?
Well, they had this requirement in the method part 5 when the top of the balloon has inflated, so it's 10 centimetres over the conical flask. So that's their stopping point.
Yeah. Okay.
And so it was the time taken. So it was that was how they measured the rate. So that's why there's 2 points in part C.
Mm-hmm. Yeah.
And then the relationship. So the rate is proportional to the temperature. I'll get myself into trouble over this. Is that right?
Yes.
And then it's a classic rate question with temperature. As the temperature increases, kinetic energy increases, proportion of collisions with energy greater than activation energy increases, and frequency of collisions also increases. There's heaps of marks there, but kinetic energy is always required, and proportion, that wonderful word proportion, of collisions with energy greater than or equal to activation energy.
Yeah. Do you think they have to mention both things, both the increase in proportion and collision frequency?
I would always tell students to do it just in case.
Yeah, I would. That's probably one thing that you have to be aware of if you're sort of new to this is, you have to even though the proportion factor is the more significant factor, the increase in collision frequency also does occur. So students do need to mention both things, unless the question says, you know, which factor is more important, which may come up sometimes.
Yeah, yeah. And then we get to part 2 of D, is the graph. Sorry, I love that graph. I always make jokes about graphs like that to my students. As the temperature increases, it does appear that the time taken for the reaction to get to that particular stage does decrease. It's just a dodgy graph, the way they've joined the dots.
Yeah, and I think with students would need to quantify their answer in some way.
Oh yes, so to say at the
you know, so
45 degrees.
Yes, that's right. For 45 degrees, it's around 50 seconds, and then when it goes to 5 degrees, it's 80 something seconds. So it's the time taken is increased.
It would be wise to say that, although it is only 1 mark. So, and they might get away without it. 2 ways in which the graph could have been presented differently. So we identified that the horizontal and vertical axes needed to be swapped.
Yeah, got to switch them around.
Yeah. And try to draw a line of best fit rather than joining the dots. And if you want to actually represent rate, as George has correctly said in the chat, to graph temperature versus 1 on time.
Yeah.
But the thing is, that graph was a graph of experimental results. So we were talking earlier about the fact that it's not the process data, it's just the raw data. So while, yes, it would be good, it doesn't have to be 1 on T at this stage.
No. Lee has asked, would you identify the 25 degrees as anomalous or an outlier?
Well, yes, I would. I'm not sure whether it's an answer to the question, though.
No.
In which
talking about how to present the data better.
Yeah, well, if you did a line of best fit, you'd just ignore that one.
Yeah, you probably yeah. So that probably would be one thing, adding a line of best fit.
Yeah. And then changes to the experimental method to improve the precision. I felt that the way the balloon was being involved was just crummy. It doesn't look to me as though it's going to be precise. This business of 10 centimetres over the conical flask would be extremely difficult to monitor. So when I was looking at that, I thought, well, how about don't use the balloon, have the flask on a balance and measure the mass loss.
Yeah, absolutely. Even just something, we were just thinking even something simple like using an analytical balance to measure the mass of calcium carbonate to 3 decimal places is more precise than what they're doing so far.
That's true, because it was just one significant figure.
That's right.
And it was very small too. So it was a small mass. And so, mind you, what are we looking for? Precision? Yeah.
Yeah.
A larger mass would help precision.
Yeah, so I think with your comment there, George, that would probably be an inaccuracy thing. So probably maybe not a precision thing about attaching the balloon after the acid is mixed with the calcium carbonate.
Yeah.
And allowing some of the CO2 to escape.
Yeah. Displacement.
Yeah, a gas cylinder.
Yeah, displacement of water doesn't work that well with carbon dioxide because the carbon dioxide dissolves in the water. So that was a comment from Joe.
But Lanna, I suppose it's still maybe more precise than the balloon method.
Which one? The
carbon
even dioxide?
Well, yeah, whether you're capturing it by displacement or gas syringe. Well, certainly by gas syringe.
Gas syringe, definitely yes, but I don't think displacement would work. I think the carbon dioxide would dissolve in the water.
Okay.
Nick has raised the point. The question is whether 2 changes are to the method already. to changes that could be made to the experimental method to improve the precision. So I always feel that when they talk about that, they mean the method as it's written there, and that the students are free to sort of pick anything from there that is relevant.
Yeah. Besides, yeah, not to the extent of changing the reaction. Yeah, I don't think they would be asking for changing the reaction.
No. No. Okay, so now I wonder which pat that is. There's a pat at the bottom there, but we don't know which pat is being cheeky. So we'll move on.
Yeah, yeah. Unless there are any other pressing comments on question 9.
No. Question 7. We'll jump to 7 because it was more popular than 8. We'll come back to 8.
Yeah, we'll come back to 8.
So question 7, the egg question. It's a very thematic paper. There's questions that just have a great big theme and they stick to it. You could almost say the paper's all about carbon dioxide. Okay, so do you want to start off?
No, I think you should lead with this one, Lanna, because you taught me something about cooking eggs.
Okay, so when I read this question, it appealed to me, even though I would never do it. So we, as students, the students know that adding an acid will denature proteins and increasing the temperature will denature proteins. So what the question has said in part A, using your knowledge of chemistry, explain why vinegar is sometimes added to the water to produce a poached egg with a runny yolk. So the idea here is that the vinegar, they probably have to put a fair bit of vinegar in there, but let's not, once again, let's not split hairs. The vinegar will denature the protein in the egg white, and you either won't need to cook the egg for as long as needed, because with a poached egg, and once again, there's a few cultural issues here. I hope the kids understand what poached eggs are like. The poached egg needs a white that's solid and a yolk that's runny. So if the white has been denatured and has become solid in the presence of the vinegar, you don't need to either cook it for as long or to cook it at a higher temperature. I guess the length of cooking is the thing probably they'd be interested in.
I think it's the length of cooking.
Yep. So you cook for fewer minutes, you don't cook the yolk, so it ends up runny, but your white is solid. Some of the cultural things and the readability for EAL students, it's been bothering me this year. So I hope that most students would be familiar, and most teachers, when we're, yes, well, I agree, George, that's just what I said.
I mean, the examiners have tried to explain what a poached egg is in the first sentence.
Using end circles. Once again, EAL. But yeah, they've tried to explain it, and most chemistry teachers would talk about egg white as an example of a protein that we can denature. Most of us would.
All right, so looking at the next one, which is, again, looking at the principles of chromatography. Again, there's 3 marks there. And again, as I said earlier on, there's probably about 5 or 6 things that the examiners will accept. And the students just need to tick off probably about 3 of those things. So I'll run through a couple that I've got. Lanna, jump in if you've got a couple of others, or in the chat if you've got a couple of others. So certainly, you want to be talking about the fact that they'll have different retention times. So we need to there's different retention times for the different methyl esters that are produced from the different fatty acids, and that you can identify them by comparing the retention time for those methyl esters with some standards. And so yeah, then you can work out what the methyl esters are and therefore what the fatty acids are. So another thing would obviously be peak area, indicating the relative amounts of each methyl ester. And then that will allow you to work out then the percentage of each fatty acid that's contained in the egg yolk. And then to actually get the quantification, you need to have a calibration curve linking together peak area with concentration of or amount of each methyl ester. Anything else,
well,
Lanna?
When I first looked at this question, I mean, I agree that those parts are what students would be expected to know because they are the basics of what they've learned in their course. But the other basic, of course, is just talking about how chromatography works. When I read principles of chromatography, I think, oh, you know, differing attraction to the stationary and the mobile phase, adsorption, desorption at different rates, the ability to separate parts of a mixture. So there possibly would be allowance for that too amongst the marks. Yeah, so lots of possibilities, lots of space. You know, it's good that they had those lines there, but they had lots of blank space underneath for the students with large writing.
Yeah.
Okay, on to the next one. Part two. Go on, Drew, you can do it.
Yeah, so there's quite a bit of, I suppose, expectation in terms of interpretation, analysis of the data in Table 2. So I guess the opening point is the students hopefully can pick up that when you go from palmitic to steric, there's an increase in the size of the fatty acid, and it causes a slight increase in the melting point. But then when you go from palmitic to palmitoleic, same number of carbons, but one carbon-carbon double bond, it produces a huge decrease or relatively huge decrease in the melting point. And so therefore, the students are meant to pick up that having double bonds in the fatty acid has a bigger impact on the melting point compared to a longer carbon chain size. And so, yeah, from that logic, looking at they're meant to look at the structure of the fatty acid in the data booklet, and arachidonic has 4 carbon-carbon double bonds. And so therefore, it's probably going to have the lowest melting point. And so therefore, probably also the lowest flash point that it's asking about? Yeah. That would be sort of the logic behind it. So yeah, arachidonic, 4 carbon-carbon double bonds. The molecule is more kinked. So discussing the structure of the molecule, and then discussing, of course, how the molecules don't pack together as well. So there are weaker dispersion forces between the molecules. So a lower flash point.
Yeah. This is one of these questions where it's really important for students to name the type of bonding, to talk about the impact of the bonding on the melting temperature and on the flash point. And the structure is the pointing to the double bonds versus the saturated fatty acids. So if you're going over this question with your students next year, that would be a classic one to say, look, we're doing chemistry. It's all about the structure and the bonding. So they tend to forget it, especially if they're doing another science, and they sort of get distracted. So thank you, Drew. We both had no trouble. Hopefully no one really needs us to go over C part 1, simply that we decided it was C51H9206.
Just to interrupt, George has asked, do you think they need to discuss the melting points of all the fatty acids in the table or just the top 3?
Well, it said, explain your answer in terms of both the melting point trends shown in table 3. Now, I think because they said shown, that it's the 3. because they are the 3 melting points that are shown. And then they're wanting, they want separately to give the fatty acid with the lowest flash point, and that's where your answer, Drew, comes in.
Yeah.
So I think the discussion is asking for only the ones shown and the structure and bonding. There'd be no harm in them extending down into the structure and bonding of the others, but we've got no idea actually what the melting points of oleic, linoleic, etc. are.
No.
So they can't expect a prediction or anything. So I agree with George. Trend. Yeah, I agree, Sophie, but the thing is, the trend shown, what's shown, the trend that's shown between those 3. With the flash point, Melissa's asked whether the trend for the flash point would be the same. Once again, they're not asking for the trend in flash point, they just want you to identify the lowest flash point, the fatty acid with the lowest flash point. So they might not even have wanted any discussion of the trend, but usually intermolecular forces are the pointer to both the melting point and the flash point, and most students would follow that through.
Yeah.
Nice iodine number question at the end there, calculation, so don't think we need to go over that. So if there's nothing else about question 6, it's a note from the data, impact is greater than the molecule length. Can I ask again, is that Pat Sanders or Pat O'Shea, or a different Pat again? I feel like I'm asking the spirits. Who just wrote that last
Maybe
comment?
neither of those 2 Pats.
Might be.
Pat O'Shea did that one.
Thank you, Pat.
So
Excellent.
they look like they're looking for you to notice that the melting point dropped a lot more when you put a double bond into those 3. So
Yes.
I expect the marking scheme would reflect that they would want you to state that you're picking that hits a more significant factor than the length of the molecule.
Yes.
Yeah.
Yes. We agree. We agree. All right. Now, well,
Done. 8, is that the next one?
Yes, 8 was the next most popular. Oh, yes. This is my page that's got scribbles all over it. Crossings out and scribbles and double guesses. Well, I'll start off with A.
Yeah.
I'll start on safe ground. So this is one of those cases, and students often don't think to talk about what is not present.
Yeah, that's right.
So the indication in the region 3,100 to 4,000 is that there are no OH alcohol bonds. So it's really important when you're teaching this stuff to say to the kids, it's just as valid to say what's not present in an infrared spectrum within reason. I mean, obviously, you're not going to say, oh, there's no NH bonds there, obviously. But yeah, there's no OH alcohols.
So that's enough for 2 marks?
No,
Lanna?
and I would have finished off with saying, because if it was there, there'd be a peak in the range 3,200 to 3,600.
Yeah, okay, yep. So that's the reasoning.
Yes. So that's the reasoning, should have been a peak if it was, and it's not. Okay, so then over to you.
Yeah. So I sort of, I approached this initially as a student would. I just thought, okay, what has that molecular formula and has a double bond in it? And again, I haven't considered any of the information in part C yet. And so I've just gone initially with the aldehyde and then also the ketone. And I feel like that's enough for 2 marks, even though it doesn't match up with the subsequent data. They're just 2 possible structures that fit the information provided so far. No, that's sort of, I'm happy to open that one up for discussion. People might say, no, you need to have a structure that's consistent with all the information. What do other people think?
Jason Gowdy's saying, yeah, no, true. Although he says you can't be testing on things you haven't read yet.
Well, see, the thing is, you'd say, oh, they've had their 50 minutes of reading time, so they've looked through the whole exam.
And I'd certainly typically tell my students to read the entire question before they attempt to answer it.
I think they'll be quite generous with this one, because I think quite a few students will not get the actual structure, especially as it's not a structure that's one of the ones they're supposed to know. You know, like it's got an ether and an ether link in it. And so I think that they'll be quite open to those suggestions at that point, because then I think there'll be quite a few who don't get anything, who aren't able to, even if they had the knowledge, aren't able to access that final 3 marks.
Yeah.
Well, they might access some of it, I feel.
Yeah. I mean, Peter's got a good point that the absorbance band at around 1680, I mean, it could be a C-del bondo, it could be a carbonyl.
Yeah.
So that might be prompting some students to think, you know, the structure could contain a C-del bondo.
Oh, absolutely. And it did say it said a double bond. It didn't stipulate what sort.
Right. That's
so
right.
Joe said, can it refer to either? Yes, it could at this stage.
Yeah, at this stage, that's right.
Yeah. And I'm sure the markers meeting will have considered all those options.
Yeah.
Yeah. So then we turn the page.
Yeah, and we have the Nmr spectrum.
Yeah, and we've got 3 peaks, and that's when the wheels fall off, if you're a student. So what you find, I was actually trying to do this as a student who'd become very attached to my ketone or aldehyde, and I was having a lovely time justifying it in terms of that. And I had a statement about the number of peaks in the hydrogen NMR. I had a statement about the peak areas. And then I fell in a heap because I wasn't able to justify them as being singlets. Now, contrary to what Melissa said, I suspect that if you were arguing successfully about the information, even though it may not actually match the right answer, I think you'd get a couple of marks in the last part.
Or alternatively, it doesn't actually ask you to draw the final structure.
No, it doesn't.
So you could just analyse, I hadn't even really noticed that, but you could just analyse the data, you know, 3 single peaks means this, the relative peak areas means this, etc.
And the chemical shift, I thought, was perfectly consistent with the presence of a carbonyl group in proximity. So I was feeling quite good until I looked at the singlets and went,
Yeah.
Yeah, they're all singlets. That's the tough bit.
Yeah. And it does say it's high resolution. I reckon a lot of students would miss that. Yeah. So, I don't know, Drew, do you want to add anything?
Yeah. So I with my approach to it was I just sort of gave very general answers saying, you know, 3 peaks just means that there's 3 non-equivalent distinct hydrogen environments. So I didn't actually match them to any particular specific hydrogen environment. I just sort of went more general. Yeah, I hope that would be enough, because I don't think it wasn't asking us to match data to a particular hydrogen environment or whatever on a particular structure.
We've had a query from Pina. What is the actual structure that matches it perfectly? So you had that written down, didn't you, Drew? Have you still got that picture?
Yeah, I could maybe do a screen share. Let me just scroll down to the right bit and I can do a screen share. So yeah, it's an alkene. It's an alkene ether. So let me just scroll up and get the right bit. And I can quickly do a screen share so people can see the structure.
A branched alkene ether.
Yes, a branched alkene ether. There we are. Yeah, so you know, you can look at, you can actually go to the website where the Spectra comes from, and yeah, again, if you don't know about that website, it's a really great resource to use when you're teaching spectroscopy. It's a great, you know, that's where you get all the spectra for the different molecules. And
sorry, Drew, was that ChemSpider?
no, it's not ChemSpider. It's a sort of a Japanese repository. It's in English, but they're run by a Japanese organization.
Maybe you can share the. Yep. Thanks, Nick.
I'll try putting up the semi-structural in the chat.
Yeah,
Oh, don't worry, Melissa. We're nearly there.
Nearly there. Here we go. So I'll just quickly share my screen for about 5 seconds. So yeah, you can see that's the structure of the molecule. So all the hydrogen environments are distinct, and they're all singlets.
Mm.
There's no hydrogens on an adjacent carbon. So yeah, so I'll just stop that share. So there you go.
Luckily, they weren't asked to actually. Yeah.
You only said not screen sharing, Drew. Did it not come through?
Oh, I saw it.
I did in the end.
Oh, thank you.
Okay, no worries, Leonie. Thanks.
There's always just a bit of a delay, that's all.
Didn't students have to determine the structure? It's a fair question. Yes, yeah, Braden's saying what we were saying, that as long as you could interpret the data, then that was fine. And Pina needs more sleep. Clearly this is getting to her. And there we have the link. So let's move on. Now I'm wondering, before we do any part B, because we're getting close to the end, a lot of people were concerned about question 28 in the multiple choice. Does anyone want us to discuss that rather than doing question 4?
Elena, I think that's a good idea, because we've only got about a couple more minutes and then we'll wind up. So I reckon if you just do one multiple choice, and then we might have to leave it at that.
We'll do question 28 because this was the one, and I'll try and share this time. This will be fun. Okay, hang on. I do that.
I'm sure everyone out there and their colleagues probably had a great chat about this question.
Yes, there it is. So question 28 was, right. Oh, no, that hasn't shared, has it?
No, it has shared.
It has
we
shared?
can see.
Okay.
I think we can. It doesn't matter. We can see it.
You can see it. Okay.
We can see it.
All right. So question 28 follows on from 27. Strangely enough, weird world we live in, and we'd worked out that there was a combustion reaction going on. So we had the combustion of both the ethanoic acid and the methyl methanoate, and they had different enthalpies of combustion, and those were given to us. And when you look at those, of course, because they're isomers, they have exactly the same products. So they're both ending up at the same enthalpy or energy level. And so that means that they're starting at different levels, and the methyl methanoate is starting at a higher energy than the ethanoic acid. The different delta H means that when you burn your methyl methanoate, more heat energy is released, and so the combustion gases are hotter. Now, that's all very well, and you're going along saying, okay, yes, the methyl methanoate is hotter, and so you cleverly select A. But the problem is the question asked the combustion of ethanoic acid.
That's right.
Would be, and we want the cooler. And I believe that a lot of students are basically going to get caught by what I laughingly refer to as exam pixies, and they're going to make that slip. And they'll have selected A, they'll have recognised that the chemical energy of the product gases is identical, but they'll have been talking about the hotter methyl methanoate rather than the cooler ethanoic acid product.
Yes.
So maybe I'm not even looking at the poor old students who didn't even understand it was the product gases.
Yeah, and particularly your EAL students are going to probably have found this one very tough. And Pat has a good point. It's more like an English comprehension question.
Yeah, it really is. But something else I said to Drew when we were going over this was that one thing I wasn't doing that I insist on my students doing is I didn't have my highlighter out highlighting the important parts of the question. And I think a good student would actually highlight the important parts and maybe wouldn't have missed the ethanoic acid.
Yeah.
So, yes, I agree with Pat O'Shea. The multiple choice in general was hard work. Hard work for a student whose English is not the best.
Do we have time for one more, or?
I think that's it.
That's it.
Right.
But what we can do is we can continue discussion. And what I'm doing now is typing and talking at the same time. For those of you who aren't already on it, I've just put the link up to the ECCN Facebook group. I think we can continue there. If you've got any other questions, you want to chat about other things that we haven't had time for today, I think that'd be a great place to go. I asked Lanna and Drew to do a job today that I think is pretty tricky, to speculate on what they think the marking scheme is going to look like. And of course, that's an impossible task. I think you've made a triumphant attempt at doing that speculation. And those of you who are marking, you know, you can see tomorrow whether how well Lanna and Drew have done on predicting the future and seeing what actually happens. Lanna's final point, I think, is like if I was going to tell you something that I think you probably already tell all of your students to do, that lesson of read the questions carefully and, you know, using a highlighter. I mean, there are so many examples here that a few people have said about where students who are don't have English as their first language would have found things on this paper to be tricky. And so reading the question carefully is really important. For those of you who are not, I really highly recommend trying to sign up as an exam marker for future years, because you will learn so much about ways to teach your students how to do exams, which of course is, you know, it's an important skill in doing chemistry. So I would like all of you to thank me and join me in thanking Lanna and Drew for this discussion. I also want to finish up by saying that this year has been, I know that I have learned a lot about teaching this year, and I've learned a lot about educational techniques, and I've learned a lot about you know, doing things in different ways, and the November lectures this year has been experimental. I think there's been some things about it that have been really good, and some of you have given me some great feedback that's reinforced that. This is the first year that we've had international attendees at the November lectures, and we've had you know, a couple of dozen people from interstate come online to the November lectures. I've had some really useful feedback from teachers in regional areas who've, you know, got little kids and find it hard to drive to Melbourne to come and do PD. So I'm going to be sending a survey to all of you that will help us think about what we're going to do for the November lectures in the future. And I think that this, I really like doing in-person PD, but I think that we might be looking at some, you know, some dual delivery and working out ways to do that in the future. So you'll be getting a survey link for me in the in the future, and thank you, Lee and Nick, about talking about the food. We do try to make sure that there's very good food at our conferences. So I would like to thank all of you for coming as well. There's been about twice as many people sign up for the November lectures this year as there have been in previous years. So that's been really good to see as well. So thanks very much, everyone. Thanks for coming along. Thanks again, Lanna and Drew. And see you in the future.
Thanks, Mick. Thank you so much, CEA, for organising.
Thanks, Meg. Bye.
Thank you.